Well, welcome back. This is unit 9.3 or 9.4, I think I should say. And this is calculating pH using Ka and Kb. And these are all of weak acids. Our last unit, we talked about strong acids. These are weak acids. All right, so as I mentioned in the previous section, we examined the concentrations of hydrogen ions and hydroxide ions and the pH of only strong acids and bases. Well, that's a very short list because there's only 6 strong acids and 7 strong bases. So most of the acids and bases are weak, and that means that they only ionize partially in water, less than 100%. So in this section, we're going to be combining the concepts from our previous 3 sections. We have 4 scenarios that we're going to go through, but before we do that, let's remember what Ka is. All right, so here we have an equation, an acid, and it dissociates into hydrogen ion and the anion, and in this case, it's NO2. So remember, writing any K expression, KEQ expression, is going to be the products over the reactants, the concentration of the products over the concentration of the reactant. So here we have our product. So this is H plus and NO2, the concentrations of those two multiplied together, divided by or over the concentration of the HNO2. Now, in our previous section, we didn't have this because it was a strong acid and base, and that means it dissociates 100%. So we would have 0 of this, and then anything divided by 0, well, you can't do that. So strong acids and strong bases do not have a Ka value, but weak acids and weak bases do. So the Ka value is this. And the only reason we use A here is because we're talking about an acid. So a few sections ago, we're talking about KSP. That's the solubility product of slightly soluble ionic salts. And so this is the same, the KEQ for an acid, so it's called Ka for acid. Now, when we generally write this, you're going to see H for the hydrogen, but we're going to substitute A here for any anion that bonds with the hydrogen. So A is an anion, and then the acid is going to be H plus that anion here. So you're going to see this written a lot, and I'm going to use it a lot. Okay, now for a base, we have NH3, and that dissociates into, when we mix it with water, water gives up one of its hydrogens, so we're going to add a hydrogen to this, so we're going to get NH4 plus, and then what's left of the water is the OH. So products over reactants, we're going to have the NH4 concentration multiplied by the OH concentration, divided by the reactants, which is the concentration of the NH3. This is called Kb, because this is for a base. Okay, and we're going to use these to solve these 4 scenarios. All right, here, scenario 1, we're going to calculate the pH from concentration and Ka. So we're going to be supplied with the concentration and the Ka. Now, because this is a weak acid, we have to have a dissociation equation. All right, so let's fill in what we know here. All right, so we have our concentration, 0.5 molarity. And the Ka doesn't go in this ice chart. We're going to use that later. So remember, initially we have this, and 0 of this, and 0 of this. Now, when this dissociates, this is going to go away. So we're going to have minus, and we don't know how much, so let's just call it X. And then we're going to gain this, and we're going to gain this, but again, we don't know how much, but we do know the ratio. It's 1 to 1 to 1. So if this goes down by X, this is going to go up by X, and this will go up by X because it's all 1 to 1 to 1. And then the E, the equilibrium, what we do is we just combine the initial and the change. So here we have 0.5 molar minus X. 0 plus X is X, and 0 plus X is X. All right, and so the equilibrium here is where we write the Ka expression. So we have Ka is equal to 0.5 molar. Oops, products over reactants. So let's erase that. Okay, so product, that's going to be X times X over 0.5 minus X. Okay, so let's simplify this. That's going to be X squared over 0.5 minus X. Now, what I want to tell you here is that this X is going to be so small that it's really not going to affect significantly the significant digits of this 0.5, because normally these dissociations, since this is a weak acid, are really, really small. So they're like some number times 10 to the negative 3 or 4 or 5. And because that's such a small number, it's not going to affect this number right here significant digit-wise. So we're going to have to make an assumption here to make this math easier. Let me go ahead and finish writing this out. In order to make this math easy, because here is really your math equation where we're going to solve for X. And because we have X here and then minus X here, if we left it like this, we're going to have to use the quadratic equation to solve this. And I don't want to do that. I know you don't want to do that. So let's assume that we can drop this X because it's going to be so small, it's not going to change this molarity, this concentration, significantly because it's so small. Now, when we leave that out, now it becomes an easy math problem. So here we just have to multiply both sides by 0.5. So we're going to get, oops, hold on, 3.5 times 0.5, 1.75 times 10 to the negative 4 is equal to X squared. Now to get rid of this, we're just going to take the square root of this. Okay, and so that's going to leave X is equal to 1.3228 times 10 to the negative 2. All right, so that's X right here, same X. So this is our hydrogen ion concentration. All right, so thinking about what we learned in our last section, we know that pH is equal to the negative log of the hydrogen ion concentration. So if we know the hydrogen ion concentration, we can take the negative log of this, and that's going to give us our pH. Okay, so that's going to be our answer for here. So negative log of that is going to be 1.88. Okay, and how many sig figs? 1 sig fig. Okay, so it's going to be 1.9 for our pH. Because remember, the decimal places in the pH are the sig figs. So it's 1.9. All right, so that's scenario 1. Now let's look at scenario 2. Scenario 2, we have pH and Ka. So we're going to calculate the concentration from pH and Ka. All right, so here, right here is what we need. Let's call this M because it's a concentration. That's what we need. That's what we're shooting for. Now we have our pH. Well, again, let's think back to the last section. pH is the negative log of the hydrogen ion concentration. If we know pH, we can rearrange this. Let me write pH here. To be 10 to the negative pH is equal to the concentration of the hydrogen. So if we know the pH, we can do 10 to the negative pH and get the hydrogen concentration here at equilibrium. All right, so let's do that. So 10 to the negative 3.30, and that's going to give us 5.01 times 10 to the negative 4. And since this is 1 to 1, this is going to be the same. Okay. And this is x, so we can go ahead and work backwards here. Fill that in. Fill this in. This is 0 and 0. Okay, so this is actually plus that and plus that. Okay, so remember on your ice chart, we have negative because this goes down by that. So 5.01 times 10 to the negative 4. And these are all 1 to 1 to 1. That's why these numbers are the same. 1 mole, 1 mole, 1 mole. Okay, and so this is m minus 5.01 times 10 to the negative 4. All right, so remember this is the Ka expression. We have a value for Ka, so 6.5 times 10 to the negative 5th is equal to this times this, so it's 5.01 times 10 to the negative 4 squared over m minus 5.01 times 10 to the negative 4. So we just have one variable here now. Okay. So we can solve for m. We can solve for this concentration. Now the algebra gets the math gets kind of intense here. So let me go ahead and work this out. Okay, so to get rid of this here, so we just have this is equal, we need to multiply both sides by this denominator. So we have 6.5 times 10 to the negative 5th times m minus 5.01 times 10 to the negative 4th. And that's equal to 5.01 times 10 to the negative 4th. So now we need to distribute this to both of these terms. Okay, so we're going to get 6.5 times 10 to the negative 5th m. This times this is negative. Okay, and so we have 6.5 times 10 to the negative 5th times 5.01 times 10 to the negative 4th. So we're going to get 3.2565 times 10 to the negative 8 is equal to times 10 to the negative 4th. Okay, so here we have our number with the variable. So we need to take this and move it to this side. So we need to add this to both sides. And that cancels it here. So 5.01 times 10 to the negative 4th plus 3.2565 times 10 to the negative 8 is, let's do 6.5 times 10 to the negative 5th on this side. This is going to be equal to, oh, that's m, right? 5.01 times 10 to the negative 4th. Because this is such a small number, 10 to the negative 8th, it didn't affect this number any when you add them together. Okay, but technically we had to do that. All right, so now if we divide both sides by the 6.5, we're going to get m is equal to 7.708. Okay, 7.708 as our molarity right here. Okay. All right, so that's calculating, working backwards essentially is what that is. All right, scenario 3, we're calculating the Ka and we're given pH and this says H. That's not true. We're given pH and concentration. Okay, so that's just a mistype. All right, so we're calculating the Ka from the pH and the concentration. All right, so concentration, we have 0.100. And pH means we have this right here. So 10 to the negative 2.27. 5.4 times 10 to the, and I'm rounding here. I should not be rounding, so let's not. 5.370 times 10 to the negative third. 5.370 times 10 to the negative third. That means that this also goes here. This also goes here. This is 0. This is 0. Okay, so this is going to be negative 5.370 times 10 to the negative third. So here we have 0.1 minus 5.37 times 10 to the negative third. Okay, again, this is your Ka. So we have products. And that's squared over reactants. 0.1 minus 5.370 times 10 to the negative third. So easy peasy, it's just a math problem now. We can put that in our calculator. Okay, and I get 3.047 times 10 to the negative fourth. How many sig figs? We have 2 here and 3 here, so 2 sig figs. So this is going to be 3.0 times 10 to the negative fourth is equal to our Ka. So this one was an easy one. Okay, one more. Scenario 4. This time we're going to be using a base. So we're going to calculate the hydroxide ion concentration, which is right here. Okay, using pH. And pH. We're calculating this and the pH using Kb and the concentration of the base. So we have our concentration of the base here. Here's our Kb. Okay, and so we are going to get this concentration here. So this is going to be x squared over 0.5. Now remember, this is minus x. Now remember, x is so small. When we subtract it from here, it's not going to change this number significantly. So we're going to leave it out just to make the math easier. All right, so here is our equilibrium expression here. So we have x squared over 0.5 is our Kb. So we have a concentration, a Kb. Oh, this is equal to 4.4 times 10 to the negative 4. Okay, so here is our math right here, and we can solve for x on this. All right, so multiply both sides by a 0.5. That's going to give us 2.2 times 10 to the negative 4 is equal to x squared. And then take the square root of that to get rid of the radical here. Is that called a radical? Exponent. Okay, so the square root of 2.2 times 10 to the negative 4. All right, and that's going to give us x is equal to 1.483 times 10 to the negative 2. All right, so that's the concentration of your x there. That's the concentration of your hydroxide. All right, so let's remember back. If we have the concentration of our hydroxide and we take the negative log of that, okay, that's going to give us, let me erase this side, our POH, right? POH. All right, so let's take the negative log of that. Okay, and that's going to give us a POH is equal to 1.828, 829 really. Okay, and then 14 minus POH is equal to pH. So if we take 14 and subtract that answer, we're going to get 12.17 is our pH. Okay, and how many sig figs? 2 here, 2 here, so 2 here. So 1.171. This is 171. So this one's not going to do anything to that 7. So pH is equal to 12.17. Okay. All right. So we calculated the OH, the concentration of the OH. It's right here. Okay. And we calculated the pH right here from the hydroxide ion concentration. All right, so that's scenario 4. One last thing before we go is percent ionization. Occasionally you're going to be asked on these questions, what is the actual percent that this acid or the base dissociated? Because we know that strong acids and bases dissociate 100%. And if it's not strong, it's weak. So weak can be anything from a 0.1 all the way through 99%. So what exactly is its percentage ionization? Well, remember, a percent is a part over a whole. So the part is the concentration of the hydrogen or hydroxide, right, divided by the whole concentration of the acid or base initially, whatever it was initially, okay? And then multiply that by 100 to change it over to percent. Okay, so that's it. So it's just the concentration of just this ion divided by the concentration of the acid or the base, the whole thing, part of a whole, multiply by 100, and you're going to get your percent ionization. All right, so that is it. Make sure that you slap that like button right across the face. Make sure you give me a thumbs up, a subscribe, and if you want to know when I put videos on YouTube before I get them into Google Classroom, then just poke that notification bell, and we will see you on the next video.